Okay guys, thanks for coming to my review session on a very short notice accelerated schedule. And thanks for those of you watching at home. Sorry I couldn't get a good time for everybody. But just to give you a little update on where things are at, I am going to be leaving town on Thursday, and I will still be in contact through email daily, so I can answer questions, and I will set up some times when you can reach me by phone as well. I haven't quite decided exactly what the times are yet, but I'll let you know in class tomorrow, and so you'll be able to call me if you have any questions. And the final is on next Wednesday, December 18th at 5 o'clock. I have found a proctor for that final who doesn't have a real tight schedule. So what I may do, I'm going to write the final to be completable in 2 hours, but I'm going to let you guys work beyond that. I imagine. I will check with the whole class tomorrow, but I imagine that there are no... Are there finals after that time block in the evening? Like, is it possible somebody would have a final, like...
I mean, unless they have a 7 o'clock class.
7 o'clock class.
Okay, so if somebody had a 7 o'clock class, they might... Okay, I'll have to check with the class, because I obviously don't want to put anybody in a conflict of time. But if there's no conflicts with the time, then I might... Because I don't think I know anybody who's taking a 7 o'clock class in 3... Oh, you are? Yeah. So it doesn't work for you? Okay. All right, so that might settle that matter. Okay, good. We're getting this all resolved now. Okay, so it may not be possible to go past. I mean, I'll give you, like as usual, a few extra minutes at the beginning and the end. The person who's coming into proctor has no limitations on time, so that will not be a problem. Let's see. It's going to cover everything that we've covered, including all the way through the last class, which is tomorrow. We're going to do the fundamental theorem of calculus in our last class, so that's obviously going to be important. On the final, there will be a slight emphasis on the material since the second midterm, or since the third midterm. So by slight emphasis, we're just talking about those last 2 or 3 sections. So maybe a slight emphasis on the integration. This would be, sections 6.3, 6.4, 6.5, pretty much. Okay, those were not covered on any of the midterms, so normally you might expect those sections to be like less than 10% of the whole class, but in this case, I might bump it up to like 15, 20%, something like that, covering the last few sections, just because we haven't had a test on that yet. The exams, once you're done with them, they will get mailed to me. I will grade them remotely. I won't be coming back. You won't be able to get your exam back until the spring. If you want to stop by, I can give you your exam then. But it will take me a few extra days, so please be patient, because I'm going to have to grade them remotely and then do all my grading remotely. So I apologize for that, but get them to you as soon as I can. But as far as the exam goes, oh, one other thing while I'm thinking about the grading. If you don't want me to post your grade online, what you can do is ask me to just email you your grade. I can do it that way.
A little.
Hey guys. I can ask. I can take it down. Some people don't want their grades posted online, so I can certainly take it down and just email you your grade if you want. And what else? Yeah, so but I will have to update the spreadsheet. I'm going to upweight the best part of your grade by 5% and downweight the lowest part of your grade by 5% and drop your lowest homework or quiz, which I haven't done that yet. So it's going to take a little while to get all that done. Your grade is actually probably slightly better than what it says right now online because I haven't done those things so far. Okay, let's see. What else? I've kept up all of the old... we haven't done that many group works as it's turned out, but the problem classes and the old exams, I'm going to print out, somebody asked me to print out blank copies of the old midterms, so I'm going to do that if you want to try and rework those problems. But I've kept everything up from the beginning, so you've got tons of stuff, like more than enough stuff to review. You don't really need me around giving you more problems to do. So definitely go back and review all of that stuff. As far as the exam goes, obviously I'm going to ask you to prove 2 out of the 4 theorems that I'm going to put on the exam, and those theorems will be chosen from the 7 theorems that are on that list. So if you go, one of the links on my website is 7 theorems from the course that are of a little more significant nature. They are all important results that have fairly involved proofs. And so what you should do is learn some of them. You don't have to learn all of them. You can pick and choose a little bit. But then you'll be proving those on the final. That'll be probably about 20% of the grade or so. Then there'll be, you know, the usual definitions, statements of theorems and corollaries and propositions, and that could be from anything, anywhere in the semester. So you're going to have a quiz tomorrow just on the Chapter 6 definitions, theorems, and corollaries. But then on the final, of course, anything is fair game at that point. Okay, so that's that. And then I'm just going to ask you to solve a bunch, some open-ended type problems, which if you go back to your 3 midterms, you'll see examples of the kinds of things I tend to ask. They tend to be things that aren't extraordinarily long to write out. They usually are things that I write questions that I think a person should be able to figure out on the fly, even if they didn't specifically study it, just because of if they've got the mastery of the material, then they can work with those kinds of problems. Or because it's similar to another problem that we've done before. So those are the kinds of things that you're going to see. I did post a sample final, actually, online, so you could even look at that, and that'll give you an idea of the last time I taught the class, sort of what I was looking for. So, you guys have any questions about the final, the format? I haven't written it yet. I'm going to write it very soon, but I have not written it so far. Any questions about it? I know this is so premature. It would be better, like, a little closer to the test when you've actually studied a little bit more, but it's the best we can do for now. I guess I'll take my camera to Nebraska, and if there's some great questions that come in, I'll just do a video over there. You can see my bedroom, and put up I have a little whiteboard over there I can just start writing, and then post it online. So who knows, we may get a glimpse inside my childhood home if things work out that way. So, okay, no questions though? Yeah, there's lots of stuff. You don't really have to have that many questions because I've tried to cover everything. I've also got some important themes and tricks of the trade that I posted on that final exam review sheet. How to prove that things are countable or uncountable. How to deal with convergence versus divergence of a sequence. How to use the big theorems, the monotone convergence theorem, the Bolzano-Weierstrass theorem. The limits of functions and continuity and uniform continuity. Just some different ideas on what are the important things to be thinking about with respect to all of those topics. And derivatives and integrals. So I actually think I put a little more work into this than I sometimes do to sort of write out what are the big themes and what are the typical strategies that you use to think about those themes. So this is just very general, right? Broad stuff. It's not too specific, but you might find it handy to kind of really challenge yourself and maybe challenge your classmates a little bit by looking at those themes and thinking about questions that are related to those themes. That might be helpful to sort of getting a mastery of. There's a little bit of this exam that's memorization, right? Knowing your theorems, the proofs of those theorems, and the statements of all the other results that we've learned. But a lot of this subject is sort of just having all of the solid background knowledge to be able to apply to a new problem. And that's where the majority of your studying probably should be, and that's where maybe this list of themes might come in handy. Okay? All right, so that's kind of that. Any questions at all? You can probably focus on the lecture notes more than the book. The book is great. Think of the notes as the sort of your primary source and the book as your secondary source. The book does go off and talk about tangential things that we didn't talk about, right? So you can kind of focus more on what we did talk about. If we did talk about it, and especially if we talked a lot about it or saw a lot of examples of something, those are the things that are most likely to be asked about on the final, right? So makes sense. It's just really common sense. Okay, so what I wanted to do, this is probably going to be a relatively short lesson today. in part because I need it to be short. I got a lot to do. But I do have a few, we haven't had a lot of time to practice integration lately, so I thought maybe we would practice a little bit with some problems on integration. Does that sound good? Okay, so let's take a look. You all got the handout in front of you. I like this first problem a lot, so let's take a look at it. And what number 1 says is, give an example of a function that is Riemann integrable. Well, first of all, it's always greater than 0 on the closed interval 0, 1. And we want it to be Riemann integrable on 0, 1. Okay. But if we take the function g of x to be the reciprocal of f of x, notice that since f of x is positive, then g of x is also positive. We're never dividing by 0 here. This function, we want to give an example where the g of x is not Riemann integrable. Okay, so I'm going to grab an eraser over here. Anybody have any thoughts about that? So a function that's Riemann integrable, but its reciprocal is not Riemann integrable. Or you could think about it in reverse, something that's not Riemann integrable, and then you flip it over and it becomes Riemann integrable.
I'm going to guess f of x equals x.
Okay, so what is your rationale for using that function? This is an example. What's your rationale for that?
Oh, my rationale was thinking of functions that are not Riemann integrable, which since 1 over x isn't bounded as it gets to 0, then it wouldn't be Riemann integrable. But then at the point 0, we would have f of x equals 0, so maybe f of x equals x plus 1.
Okay, so this function does not quite work because when you plug in 0, you get out 0, which means it's not greater than 0 on the whole interval.
So x plus 1.
So Joseph is going to modify his estimate here. So try this. Let's see. So now the function is definitely strictly positive. Is this Riemann integrable on 0, 1? Okay, give me any number. What would be the reasons? Or give me a reason. Why is this Riemann integrable on 0, 1? You've got several choices.
Continuous.
It's a continuous function.
Monotone.
It's a monotone function. Is there anything else?
It's a line.
It's a line. Yeah. It's definitely a line. I guess you could say, well, f of x equals x is Riemann integrable. 1 is Riemann integrable because it's a constant. So when you add them together, it's Riemann integrable. Yeah. Okay. Anyway, so this is highly Riemann integrable on any interval, actually, any closed interval. So this is no problem. What about this function now? 1 over x plus 1. I think would it help to draw the graph? Here's 0 and here's 1. G of 0 is equal to 1, and g of 1 is equal to 1/2. So it looks something, it's kind of like curving down like that. Is this Riemann integrable?
Yeah.
Why is it Riemann integrable? Can you give me a fast reason?
Monotone, continuous.
It's monotone, it's continuous, it's got all those properties.
Mm-hmm.
Darn, so it doesn't quite do what we want it to do. Okay. So, let's go back. This was the original function that was suggested, f of x equals x. And we said that that didn't quite work because f of 0 was equal to 0. But otherwise, let me ask you this, if we had, other than that issue, that f of 0 is equal to 0, would this have been a good example? So here's my g of x now. Here's 1, and now this is blowing up, right? Okay. And remember that if your function is not bounded, then it's not integrable. So this would have been great, right? It's so close to being a good example. It fails to be a good example really only because f of 0 is equal to 0. So one suggestion for how to modify it was to add 1 and shift it over. The problem with that modification was that made this bounded, and it made this thing Riemann integrable. I'd like to not restore the Riemann integrability of this. I still like this as sort of the place to start, but instead of modifying it by adding 1, shifting the graph up, is there a different way that we could modify f of x?
Piecewise function.
A piecewise defined function. Okay, so I want everybody to be thinking about this. So you want to have how many pieces?
2.
2 pieces, and what's one of your pieces?
X for x not equal to 0.
Okay, so hold on. If x is in this interval, in other words, we have one point that was giving us trouble here, which was just 0. So let's just take it out. Okay, so now when I draw my graph of f of x, I've got an open circle there, and it goes to this point, 1, 1. Okay. Now when I flip that over as a reciprocal, it'll still be unbounded, right? So that's good. And what do you want to make f of 0 equal to? Somebody, I don't want to let Joseph do all the work. Remember, it has to be positive. What's your favorite number? What's your favorite positive number?
7.
7. Oh, good. I like that number too. There's 7 right there. Okay. So we'll put 7 up there like that. Okay. So 7 if x equals 0. Okay. So then when we think about g of x is 1 over x if 0 is less than x is less than or equal to 1, and 1 over 7 if x is equal to 0. So now my graph for g has 1 over 7 is filled in here. This is g of x, by the way. Right? But it's still unbounded. Okay, so now let's go through our spiel and make sure that everything is good. So g of x clearly not Riemann integrable because it's not bounded. You move the 1 point on the y-axis down to here, it's still not bounded, right? It still blows up. Okay, so this thing here is not Riemann integrable. What about f? Is f Riemann integrable? I hope so, otherwise we're spinning our wheels here. I need a reason why f is Riemann integrable. Do you know what it is, Joseph?
Because x was Riemann integrable and we moved a finite number of points.
That's it. The theorem we did yesterday says if you take something that was already Riemann integrable and you move a finite number of its points, it still remains Riemann integrable. And we only moved this 1 point up to there. So in other words, if this point had been filled in down here, then we would have had just f of x equals x, which would be Riemann integrable. So by moving that 1 point, it's still Riemann integrable. That was theorem 6.5. Okay? So that does it. So this f of x is Riemann integrable. Okay? Is everybody comfortable with all that? This is a nice example that I almost didn't want to do it today because I thought, oh, this is a good test question. So these sorts of questions are the kinds of things you want to like quiz each other about and see if you can make sense of. Okay? So that's a good example. Anybody have any doubts about any part of this? Anything seem problematic here, or are we all good? Okay, super. In that case, there's a part B to this question. And I want to look at that next, and that's going to take a little bit more work. Part B says, if f is continuous on the closed interval AB, and f of x is greater than or equal to 0 on that whole interval, then the reciprocal function g of x, which is 1 over f of x, now this is Riemann integrable on AB. So we would like to prove this fact, okay? I'd like to prove that is true. Okay. So this is proving. So of course our example from part A doesn't apply because the function f that we ended up with was not continuous. But if our function is positive and continuous, so here's, you know, AB, your function is positive and continuous, right? Something like that. Then the reciprocal function has to be Riemann integrable. Okay? So, do we have any ideas about how we might prove that?
Theorem 6.2.
Yeah, proving something's Riemann integrable. One of the first things you tend to think of is Theorem 6.2, right? So that seems like a reasonable thing to do. Theorem 6.2 is the one that says that a function is Riemann integrable if for every epsilon there exists a partition such that UPF minus LPF is less than epsilon. Okay, so let's try it, proof. And we're going to use Theorem 6.2, which means I'm going to let epsilon greater than 0 be given. Okay. All right, we've got that. Any ideas how we can take advantage of that?
Can we say that F is Riemann integrable since it's continuous?
Exactly. F is continuous on a closed interval, so it is Riemann integrable. So we do know that. So how do you want to use that?
Since F is Riemann integrable, we know that this theorem holds for some epsilon.
Right, exactly. We can already use the theorem 6.2 for F, right? So F is Riemann integrable. That, by the way, is from the theorem we did yesterday, theorem 6.7, which says that a continuous function is always Riemann integrable. So there already exists the partition, right? See, our goal here is to come up with a partition. So somehow we've got to produce it. Now we can produce it, right? So there exists, so by, I'll just say by theorem 6.2, there exists a partition of the interval AB such that UPF minus LPF is less than whatever number we want to put here. Okay? I still have to decide what number I want to put in that box. I could just put epsilon there, but I'm not sure yet. What we want to do is show that UPG, well, hopefully it's the right partition, right? Hopefully this is the same partition that we're going to use to prove that G is Riemann integrable. So what I'm hoping is that UPG minus LPG is less than epsilon. Okay? So it'd be nice to somehow relate the UPF and the UPG somehow. It kind of we did something like this yesterday too, where you've got these two functions and you're relating the different sums. So we need to kind of think about whether we could make a relationship between these things. Partition here. So we take, say we take this subinterval right here. And this is the function f, right? This is a picture of f. It's greater than 0. And we know that there's this partition P. We've already written it down. And so right here is one of my subintervals, right? And the UPF is interested in the big M's, right? So would you agree that the big MI would be right there and the little mi would be right there? I'm going to call that big MI for F and little mi for F. I'm going to try and distinguish whether it's F or G that we're talking about. Agreed? You understand that, Ulysses? So if I were to flip it over now and look at G, of course, it's still going to be above the x-axis because everything's positive, right? Then when I take the reciprocal of this number and I take the reciprocal of this number, which one becomes bigger? Don't they get flipped around?
Yeah.
Right? So wouldn't it be fair to say that big MI for the function g is actually obtained by flipping over the little mi from f? I'm going to use that notation. And then similarly, the little mi from g is obtained by flipping over the big mi from f. Does that make some sense? So when I look here at this equation, see, I don't know what to put in the box yet. I'll come back to that. But when I look at UPF minus LPF, that's just a summation from 1 to n of big Mi for f minus little mi for f times delta xi. Agree? This making any sense? Okay, so then if I'm trying to look at UPG minus LPG, let's just start looking at this expression. This would be what? The summation I goes from 1 to n of big Mi of g minus little mi of g. I'm using the same partition, so the delta xi's are still the same, right? The same delta xi's. This make sense? I want this one to be less than epsilon. Let me put that over in the far right corner here. Less than epsilon. That's what I'm hoping for. UPG minus LPG. I want it to be less than epsilon. I'm just trying to fill in the steps here. Right? Now, so this is big Mi minus little mi times delta xi. But we just said that we can rewrite the big M's and little m's for g in terms of the big M's and little m's for f. Let's actually plug that in. So this would be a summation from 1 to n of 1 over little mi for f minus 1 over big Mi for f. And I don't have enough room here, do I? I want to get less than epsilon. I'm going to have to come down to a new line, though. Okay? Any suggestions on what I can do with it? Of course, this is the thing I know about. Does anybody see how to kind of get this expressed in terms of that? Or not even that, just even more simple than that. What would be your inclination? You have a subtraction of reciprocals. What would you tend to do with that? Just as an algebra student, right? An algebra student's going to say, I'm going to find a common denominator, rewrite it, yeah? Okay, so let's do that. So this is going to be the summation, I going from 1 to n, right, of what we're going to get here, and I'm sorry for the small writing, but it's going to be a fraction. So it's big Mi of f minus little mi of f all over little mi of f times big Mi for f. Does that look reasonable? Okay, yeah, that looks pretty good. All right, well, if I didn't have the denominator there, I'd be in great shape because I could just say over here, see this is actually sort of, oh, I forgot my delta xi. Sorry. This is basically the numerator of that summation. So I've almost got what I want. It's just I got the darn denominator in the way. If the denominator wasn't there, I would just go back and fill in this box with epsilon, right? And then this would just become less than epsilon and we'd be done. But we have a denominator there. I'm wondering if anybody knows how we might be able to handle the fact that there's a denominator. These would be